Hello. So today we're going to continue our study of cardinalities of sets. And we're going to close off this section on cardinality with the notion of countability or countable sets. So we begin with this definition, 1.3.6 from the textbook. And it says, so let S be a set. Okay. Part A. S is said to be denumerable if there exists a bijection from the natural numbers onto the set S. S is countable if S is either finite or denumerable. And we say that S is uncountable if S is not countable. It's kind of a silly definition, but it does formalize this notion of cardinalities of sets with infinitely many elements in them. So let's look at an example of a denumerable set. So, example, the set E of even integers, which we can write as 2 times n, for even natural numbers. So this is the set of 2 times n such that n is a natural number. This set here is denumerable. In other words, there exists a bijection from the natural numbers onto this set E. So we can look at a kind of short proof of this fact by finding a bijection. And it's sort of defined by how the set's defined. So it's not going to take much work to show that this is indeed a bijection. So this is like an informal proof here. So informally, let's define a function f from the naturals to E with or by f of n is equal to 2n. Okay. So under this assumption, we need to show that now f is injective and surjective. So recall that the definition of being injective, and we'll do that first. So next, suppose that f of x is equal to f of y. So under that assumption, hence, so the image of x is going to be 2x, and the image of y is going to be 2y, which that's only true if x is equal to y. So this little argument here shows that our function f is injective. To show that it's surjective, we just let, say, I don't know, z be an arbitrary element of E. Be some arbitrary even integer, or even natural number. So by the definition, so then, or by the definition of E, there exists, or then, z is equal to 2 times n for some natural number n, since it's in that set, but that's precisely the image of n under f. So this quick argument here justifies that the function that we defined by this is both injective and surjective. Thus, there is a bijection from the natural numbers onto E, and E is denumerable. Okay. So maybe next we should look at more examples. But I want to say something. I want to say that if a bijection exists between natural numbers in a set, then for each natural number, 1, 2, 3, 4, 5, so forth and so on, each of those natural numbers get sent to a unique element in the set in question. And the set in question, since the function is a bijection, each element in that set has an element that's sent to it from the naturals. So you can think of being countable or denumerable in specific, as aligning each element in the set with a unique natural number. In other words, if you have a set S with elements in, say, denoted by lowercase s, if it's denumerable, then you can label each one of those elements in the set S with a unique natural number. So if S is denumerable, then S can be written as a sequence if it's denumerable. So this is an important property of denumerable sets. Hopefully you can see that. It says S1, S2, S3, S4, dot, dot, dot. And the reason why we can do this is a sequence is just a function from the natural numbers to some values, right? So if there exists a one-to-one correspondence between S and the naturals, then for each of the elements in S, we can pair them up with the naturals, and that becomes a sequence. So if we can write out the elements in a sequence, or write out the elements in a set in a sequence, then it's going to be denumerable. Okay? And that leads me to my next example. Instead of, no, I'll use this example. The natural numbers Cartesian product with the natural numbers is denumerable. So let's think about why this might be true. We're not going to define an explicit function to do this like we did over here, but we're going to use this notion of writing the elements in a sequence, and if we can do that, then we can say that that set is denumerable. It's not a formal proof, but it's an argument or justification of why the proof would follow with inspection and the details filled in. So what does this set look like? So this is like a proof idea. So we may list each element of this Cartesian product with the following grid. Okay, so recall that the Cartesian product just consists of all the tuples that are possible by taking the first element in the tuple from this set and the second element in the tuple from that set. So we can say 1 gets paired with 1. 1 also gets paired with 2. 1 also gets paired with 3. 1 also gets paired with 4. Dot, dot, dot. So these are all the tuples from this Cartesian product with a 1 in the first entry. So then we have to move to the next number in the first set, which is 2. So then 2 is going to be paired with each number from that set, which is the set of all naturals. So we can write that out with this list. So 2 gets paired with 1. 2 gets paired with 2. 2 gets paired with 3. 2 gets paired with 4. so forth and so on. And then we move to the next number, which would be 3, and we do the same thing. So 3 is paired with 1, 3 is paired with 2, 3 is paired with 3, 3 is paired with 4, up to infinity. And this is going to continue down to infinity, continue down to infinity. So you would agree with me that this grid of numbers, this infinite grid, would indeed contain every element from that set. And our goal is to somehow write this grid as a single sequence. So the way that we're going to do that is with the following procedure. We're going to choose the first element in our sequence here. That'll be A1. And then for our next element, we're going to choose 1, 2. And we'll call that A2. And then for our next element, we're going to choose 2, 1. We'll call that A3. And then for our next element, we'll choose 3, 1. And we'll call that A4. For our next element, we'll choose 2, 2. We'll call that A5. And then for our next element, we'll choose 1, 3. We'll call that A6. And then we continue this pattern. So this would be A7. That'll be A8. That'll be A9, so forth and so on. So if we continue this diagonalization pattern throughout the grid, we're going to end up collecting every element in this grid, which happens to be every element of that set. And then if we list those out, so then we have A1, A2, A3, A4, A5, A6, we just keep on going, right? If we list out every element by this diagonalization pattern, we're going to get every element in this grid, which means there's a one-to-one correspondence between the naturals, which are the subscripts here of the sequence, and the elements of that set. So for example, 1 would be paired with the element 1, 1. So 1 gets mapped, so this function, I'll call it phi, goes down like that. And then 2 gets mapped to 1, 2. Again, the subscript represents the element of naturals as being mapped to the element of that set. And then the next element would be 2, 1. The next element was 3, 4, or 3, 1. So 4 gets mapped there. The next element was 2, 2. So 5 gets mapped to 2, 2. The next element was 1, 3. 6 gets mapped to 1, 3. And we see if we continue this pattern on to infinity, every element in the naturals is going to have a unique element assigned to it from the cross product in the Cartesian product of the naturals. Every element in there is going to have a unique element or subscript, in this case, assigned to it in the naturals. So this function that we've kind of pictorially described would be a bijection, which means that indeed this set is denumerable. Okay. And the same idea here, which also show, so the same idea implies that the rationals are denumerable. Because you can make an infinite grid containing every positive rational number, that becomes denumerable. And then you can make an infinite grid for every negative rational number, that becomes denumerable. And as we'll see in a moment, the union of denumerable sets is also denumerable. Okay. So hopefully these two examples illustrate the idea of being denumerable. That is that if you can write the elements in a set as a sequence where every element appears only once, and we have that, and every element has a pre-image is an integer value or natural number value, then this sequence is showing that it's enumerable. There's a one-to-one correspondence between that set and the naturals. Okay. So, for example, yeah, let's go ahead and kind of give an idea of why this is true. I was going to leave it to you to work on why those rationals are enumerable, but I'm going to go ahead and show it, like the same idea. It's kind of repetitive, but I think it's important to see it. Okay. Let me try this off a little bit. And I'm going to leave the definitions on the whiteboard, just so that those can always be up whenever we're doing the proofs over here. You can just reference those definitions when needed. So the next statement I'm going to say is that I claim the union of denumerable sets is denumerable. So that's my claim. And again, we're not going to get a super formal proof for this claim, but it's kind of like justify why this makes sense. So again, it's like a proof idea. So let's begin by saying let A and B be denumerable sets. Let's say denumerable about the sets. Okay. Now, by our observation that we can write denumerable sets as sequences, I can maybe say maybe comma and list elements of A and B with the following sequences, say A1, comma, A2, comma, A3, comma, dot, 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 and B1, comma, B2, comma, B3, comma, dot, 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 respectively. So these are all the elements of B, these are all the elements of A. And the union of these two sets, A and B, just consists of the elements in A and the elements in B, with possible repetition if they weren't disjoint sets. So then the elements of A and B can be listed with the following sequence. Say A1, comma B1, comma A2, comma B2, comma A3, comma B3, dot, 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 up to infinity. Okay. So this lists every element in the union, possibly with repetition, but it definitely lists every element at least once. So then this is like listing a sequence, right? Like this could be, say, S1, this could be S2, this could be S3, this could be S4, this could be S5, this could be S6, so forth and so on. In this sequence that we've defined here, it does define a function. So, for example, so let's see if I can actually write out what this might look like. So f of 1, so f is going to map the naturals to A and B. So that's what I want to find. I want to find the bijection from naturals to A and B. And I'm going to try to, like, we might be able to do this like with a formal proof. I wasn't going to actually do that. I was just going to do an idea, but let's just say, let's say that f, let's say H is the bijection from the naturals to A, and we'll say that G is the bijection from the naturals to B. And we know that these bijections exist because we're assuming that A and B are denumerable. So the function f that we're going to construct from the naturals to the union, I'm going to say that, so f of 1 is going to be equal to h of 1. So h maps the naturals to A, and the element 1 was mapped to this element A1 in A. So that's saying this is A1. So that right there is saying, so instead of like using S, I'll say that that is f of 1. And then f of 2 equals to g of 1. And g is the bijection from the naturals to B, so that should be 1. Okay. And then, what can we say? So that's f of 1, this is f of 2, that's f of 3, that's f of 4. So you can see it would be some type of, so it looks like the odd naturals are being mapped to A and the even naturals are being mapped to B. Right? So then with some work, and I guess this is still the idea, with some work, we would be able to construct a function that maps the naturals to this list of numbers, which contains all the elements of the union of these denumerable sets A and B. So that's the idea. So let me clean this board again. Okay. Dry it a little bit here. Okay. So, okay. Let's look at a theorem. So this is theorem 1.3.11. Okay. And this theorem says, so maybe suppose T is a subset of X. Okay. Now this is part A of the theorem. And that states that if S is countable, then T is countable. So recall that a set is countable if it is either finite or it's denumerable. So those are the two cases. Okay. Now, when considering the proof of this claim, we only need to really consider the case when T is infinite, right? So we may assume that T is infinite because if it's finite, then we're done. So I'll go ahead and write that out. So if T is finite, we are done. So we will assume T is infinite. So if T is finite, we are done. So we may assume T is infinite. And we're going to assume by way of contradiction that T is not countable, it's uncountable. So by contradiction, assuming T is uncountable. Okay. So we're also under the assumption that S is countable, right? So since S is countable, and we're assuming that S is infinite since T is infinite. So we're assuming that S is countable and infinite, which means it's enumerable, which means that there's a function from the natural numbers onto S so that that function is a bijection. So we're going to say let F from the naturals to S be a bijection. We know that such a function exists because we are assuming that S is countable and infinite, which means it's enumerable, which means that a function from the naturals onto S that is a bijection. Okay. So Then we can say F inverse of T, well, maybe not jumping ahead, we can say since T is uncountable, then the set X equals to the inverse of F, which, by the way, if there's a bijection, there's always an inverse. There's a function from there to there that inverts all the elements, right? You go back to your pre-images. So if we look at the pre-image using the inverse function of T, these have the same cardinality. X has the same cardinality as T, has the same number of elements, because F is a bijection, which means for everything in there, there's exactly one thing paired up with it in there. So since T is uncountable, that set X must be also uncountable. Again, F is a one-to-one correspondence between the naturals and S. T is a subset of S. And if we look at the inverse image of T under F, or the inverse function, that set is in one-to-one correspondence with T, which means that since T is uncountable, X must also be uncountable. But note, X is a subset of the natural numbers, right? Because T is an S and the inverse function takes us back to the naturals. X is a subset of naturals. And so, X has a least element, a smallest element. By the well-ordering property WAP of naturals. That's my previous lecture. Every non-empty subset of the natural numbers has a least element, smallest element. We know that T is not empty, it's infinite. So I know that X is not empty, so it must satisfy the well-ordering property of the naturals. I'll say if this smallest element, I'll denote it by A1. Right, so no, that's in the set X. So A1 is the smallest set in X right now. Okay. Next let capital X of 2 equal X set difference A1. Okay, now again, X sub 2, subscript 2, that's a non-empty subset of the natural numbers. So it also satisfies the well-ordering property of the naturals. So then again, by the well-ordering property of the naturals, by WAP, then X2 has a smallest element. And I'll call that A2. So say A2, which is an element of X2. Okay. Next, so maybe I can write this queen now. Next, let's say X3 equal x2 set difference a2. So in general, we can just iteratively apply the well-ordering property of the naturals to each of these subsequent sets. So maybe I can squeeze in a nice sentence here to describe this property. So maybe I can say in general, for I greater than or equal to 3, let a sub I be the smallest element of x sub I, and x sub I plus 1 equals to x sub I step difference a sub I. And this is for all natural numbers greater than or equal to 3. So this process goes on to infinity. And what we're doing is each of these a sub I belong to the set x, which means that if this goes on to infinity, right, we can keep on doing this forever for each of those elements, and we'll get a sequence. So hence, we construct a sequence and it's very important that we're using this well-ordering property here on each of these sets. So we can just keep on finding the smallest one and just iterate that every single set that we make is the smallest element, and we just keep that going. And in doing so, we construct a sequence A1, A2, dot, dot, dot of all elements in X. Hence, or maybe this implies, that X is countable or denumerable, say. Denumerable, comma, a contradiction. Why is that a contradiction? It's a contradiction because we constructed a sequence of all the elements in X, which means it's enumerable, but since T was uncountable, the inverse image of T under the bijection method, which is X, means that X is uncountable. So you cannot be uncountable and enumerable at the same time. That's the contradiction. So it must be the case that our assumption that T was uncountable is false. T is countable. Okay. So that will be the end of this video. I'm going to post a video that goes with this about Cantor's theorem, which involves also cardinalities of infinite sets. However, I think this theorem would be a nice standalone video on my YouTube page, so I'm not going to include it in this lecture. I'm just going to record it after I wrap this up here. Okay? So that'll be it.